just a graduate student, a PhD student in a quantum dynamics research group of Dennis Wonder. And our collaborators are Kurt Jacobs from USANA Research Lab and Jakub Mareczek and Georgios Kopas from the Czech Technical University. Actually, so I should report today about a couple of useful instruments that hopefully can help design better quantum devices by deducing simple equations of motion for open quantum systems. Okay, just first of all, a little bit of motivation, yeah, just what we are talking about. So, even a single real qubit of a real quantum computer is not just a qubit, but an open quantum system. It is a qubit coupled with some environment. Yeah. And to make a precise simulation of a real quantum system using the Schrödinger equation, we will need to consider the complex Hamiltonian, which should include the system, the interaction, and the path. And this task appeared to be computationally very expensive in most cases. And the other approach to dealing with such system is to consider a density matrix formalism, which for qubit will be just a partial trace of whole density matrix of the system. And never mind how complex open system is, if we can consider the 2x2 density matrix to describe its behavior. If we are lucky and the evolution of system is Markovian and other conditions, we can have the Lindblad form master equations for this system, which are much simpler to analyze. And our goal is to deduce some master equations, some linear equations for density matrix of the system. Yes, so find some linear operator which will govern the behavior of density matrix. And generally, we have some measurements, just some data of some data points, some time series for just elements of density matrix of density matrix of all elements of density matrix. And our goal is to find the linear equations that will balance. And this kind of task, in fact, could be, well, it is similar to the tasks that are solved with classical methods for mechanical systems. Yeah. So, but these methods that are very good developed for system identification of aerospace systems, any kind of mechanical systems, are rarely used in quantum for quantum systems. Yeah. And I want to stress that the topic of identification of open quantum systems is quite hot topic in the last years. There are dozens of publications. I can mention just a couple of them. One very solid one is by the group, as far as I understand, led by Jan Petersen. And they tried to develop the procedure, the algorithm of identification of open quantum system, beginning from the assumption of Krauss operator sum representation of the system, kind of the most general approach, and then they're going through quite complex multi-step optimizational problems, and you know, with reaching some results, and it defines a Hamiltonian, and it defines the dynamics of the system. Our approach will be a little bit as we consider the only significant assumption about system, its linearity, not necessarily the evolution, the Gauss sum operator evolution, which of course can give some weird results, but makes computation much easier. I also can mention the recent work by Dennis Bonder, Kurt Jacobs, and others. They used the linear system identification techniques to derive the Lindblad master equation, which is valid for different generated, non-generated regimes in weakly coupled quantum systems. Okay, but no, now the main body of my presentation, which is about the two separate methods. So I have two parts of the presentations, and first part is dedicated to the linear system identification, this classical method. I will go through all the steps of our data pipeline, how we process the information, starting from the short explanation about the simulation of initial data, which was done by Kurt Jacobs in US Army Research Lab. It was just a Schrödinger equation simulation with matrix product state method. Then the check of linearity of the system, that actually the core of our of my report, the linear system identification algorithm, and discussing of some results, including the minimum rank, the dependence on rank of coupling, and some tweaks to improve the convergence. And the other method is application of polynomial optimization for master equation identification. This is totally different because if in first case we assume only linearity of the system, no other assumptions about system data. In the second approach, we assume the specific Lindblad equation exists, and we even assume the rank of this equation. And we are just identifying the parameters of Lindblad evolution, having the assumptions that it holds. And it also we will also follow the same steps about how we simulate data, how we ascend the polynomial objective, which is the most interesting part, and actually using the polynomial optimization, for quite standard one, and discussing the result, which appeared to be quite robust against noise. Okay, so let's move forward here. So this is the first step of first part of the presentation. What we are talking about? What data I have? I have a data simulated by Schrödinger equation with this Hamiltonian, which includes just two-level principal system. Yeah? So it's just sum of two terms in system Hamiltonian, the interaction part of the Hamiltonian, which you see includes spectral density of the bus and the operators which act on the qubit, and actually the bus part of the Hamiltonian. And what data I effectively had? I had a time series of density matrices, which are just a partial trace of the this big solution. One important parameter of the data is the damping of the K rate. It's kind of proportional to the spectral density of the bus and the resonance frequency. And we had this time series of rho for different damping rates. So the next step is the linearity. So the major and the only assumption about time evolution dynamics of the system is linearity. Yeah? So it means that the density matrix could be expressed as a composition of some basis density matrices. Yeah? We could choose, for one qubit level system, we could choose Pauli matrices, but for our particular case, we choose other set of density matrices, which also form a basis, and which is more convenient for us because we had such a data. And so this is kind of the formula of how exactly the linear composition will look like, and we tested it for our data and found that really the error of linear decomposition is quite slow. So this holds for our data, and I can talk more about this, but let's go to the actually core of linear system identification algorithm. This is the classical algorithm of system identification for linear time independent system. Yeah? How we use it. We have the system, yeah, this black square, and we consider it has some number of parameters which totally describe its behavior, and so we have kind of a system of linear differential equations. Here it is in matrix form, and the AC, the system matrix. Yeah, so quite simple. But what is important that we don't have direct access to this. What we can measure is different set of parameters. We can measure some. We have data for some density matrices, and for us to fully describe the behavior of the system, it will be enough to consider at each moment of time all elements of all basis density matrices. They will form this vector of output, and this vector of output is of fixed dimension, 12-dimensional in our case. But the dimension of the system could be different. Yeah? It could be 3 to 30 and more. And it will depend on the character of evolution. And this rank n, which size of AC matrix, is unknown, and we will determine it. And we also should determine this AC, C, and matrices and the x0, the initial state. And we can do it if we have a sufficiently long time series of measurements of this vector y, of this output. We can determine all these parameters. Just to give you an idea, if we can rewrite this equation in discrete form, and we in fact have this discrete data, so we can introduce the operator A, which is just exponentiation of the AC matrix, and in this case, every next step of state of the system could be expressed from the previous step and effectively from the very first step of the very first state of the system. Yeah. So we can observe, and the same story is our output, which will only difference is the C matrix. So we effectively will have at least a long sequence of this of this C, AK, and X0. So this will be sufficient enough information to recover all these matrices, because on each step we have all these C and A matrices in different. I can also. Yeah. So this is actually the description of the algorithm. more exactly. I can go into detail in questions but generally we have just outputs. We form the Henkel matrix of these outputs, and we see that this matrix has this structure of product, and we can perform singular value decomposition and find out these matrices and let's go to the results, which is probably the most interesting in the first part. So what you can see on the graph, it is error of our identification. So we compare the exact dynamics which we have in initial data with dynamics given by our identified models and find out the maximum difference between elements of density matrix during all the time of the evolution. And this error is showed here by the color. It's gradient color. Yeah. The dark is the lower error, and the yellow is the highest error. And here is the horizontal axis is our damping rate, and the vertical axis is the rank of the system. For every damping rate, we can calculate models with different ranks, and then we can find the optimum rank. Yeah? These lines are actually the lines of optimum rank for different time, for different precision. Yeah? So we can say that we need some 10 minus 3 or 10 minus 5 or 10 minus 2 precision, and found the minimum rank of identified system which fulfills this demand for precision. And what we can see is that for low damping, we effectively have the rank 3. So we have just qubit by itself. So it behaves like a just qubit. You have three dimension degrees of freedom. But as soon as we introduce more and more damping, the rank of the system is going up. Yeah, and eventually we are reaching quite high ranks. So this internal rank, this internal vector X and this internal matrix A of the system are of quite a high rank. So this could be possibly even non-Markovian evolution, which is still reproduced with quite a high precision. And you can see white spaces on this graph. They correspond to unstable models when our error goes very high, which is due to the fact that in this AC matrix of the system we have sometimes a positive eigenvalues, which makes the elements of density matrix just blow up. Yeah, so it's a totally unphysical situation. But we don't have this introduced in the initial models, so such things could happen. Yeah? And we introduced some simple fix for this by just finding the eigenvalues and eigenvectors, nulling this eigenvalues, the positive eigenvalues, and reassembling the matrix once again. And in this case, we don't have these white spaces. All the models is obviously stable, but in some cases we should pay for this stability with a little bit lower precision of the model. Yes, this is what I can say about the first. And I have some minutes for the second method. It's a polynomial optimization for the blood mass equation. Yeah, so we we assume that the system should have some Leplat type evolution. This is an assumption that we have about the method.
I have a question about the first part of the talk before we move on. So, did you say you also learned you can identify non-Markovian dynamics? The first part, when you were explaining the plot, it sounded like you were saying.
Well, yes. So we are identifying the kind. So it of course depends on how we will define some Markovianity. But yeah, so we can define some dynamics, and we have no physical. We have no assumptions about this dynamics. So it could be anything actually. So we don't assume that even the chaos operator some evolution or any kind. We don't have any assumptions about this matrix except it is linear. So it would give some weird results and possibly.
So it's not necessarily in one-to-one correspondence with master equation dynamics, right?
Well, if you could say that master equation is for density, so well, yeah, it should be the correspondence. So maybe in fact we have some linear operator over y. So, so.
Thank you.
Would you mind if I ask a question?
So sure, yeah.
I was wondering, just a quick question. So this setup looks similar to something called, I think, a hidden Markov model. Would this be a more general? So a linear system identification, would that be a more general way of understanding hidden Markov models? Because there are some Markovianity assumptions there, right? So would that be an accurate statement, or what do you think?
I'm not sure, to be honest.
Looks very similar, but okay. I just want to.
We can discuss that. Oh, go ahead. Yeah.
So when you were looking at the relative error and the amount of breaks in both of your results, you had this point where it like dipped down, where previously you needed a higher rank system, and then at some point you
Yes,
yeah. And I can see the scale is not even that sometimes between your tick marks there's a large jump. So what is the intuition behind you?
Yeah. So intuition is possibly that. So we tested this. Yeah. So the major assumption for this method is linearity. Yeah? And for high adaptive rates, we effectively had other time step, which is longest time step, and possibly this error is because in the initial simulation it was some error of linearity, and if when we actually decrease the time step, it looks like the model will perform much better when we have lower time steps for high damping rate. So my intuition is that we just have not that good data for some of the points here, and if you would have a better data, it would be kind of more monotonic.
Yeah. So kind of a related question: why do we see that dip in error not for like the lowest damping rate? There seems to be kind of a sweet spot. So what's going on there?
Yeah, it could be optical, because so we are finding the darkest, the darkest, and here it more or less the same color. I think it would be a little bit different color because so the threshold not exactly depends on the color, not exactly corresponds to one particular color. but generally the point should be on the boxes of the same color.
We should probably move on to the second part. Of
Yeah, I think. Yep, I'll just do this. So it's just straightforward simulation of Markovian master equation with a standard Qt function. So data is just straightforward. The only thing is that we introduce some noise. So we just edit in W proportion some random density matrix which we consider noise. So that's always So the most important part. So our idea is that we want to find the H and A, the Hamiltonian and dissipator, such that our evolution of the system would be as close as possible to the Popovych equation. And we can do it just considering this right hand side of the Popovych equation as a linear operator. We can say that as the next step of density matrix is just exponentiation of this linear operator of the previous law, and using this identity we can just make a Taylor expansion and effectively write down this identity and force this identity in our target function. And then we just assemble the polynomials for which, so in this case, we consider 2 by 2 Hamiltonian and 2 by 2 dissipator, and we just assemble the density functions for this restriction for each point. So and then just simplifies as a whole thing. And this is almost the end. And we surprisingly had a quite good results. Yeah? So we ran for more than 20,000 examples for each noise. And this is the box plot. Yeah? So the box plot means that the 50% of the points are inside the box and 99% of the points are between these marks and the signs. Yeah? And all the rest is outliers, which are responsible for less than 0.5% of all the, around 0.5%. So you can see that yes, the results are obviously going worse with the noise, but still, even introducing the 5% of noise, W005, yeah, we still have the fidelity of identification, which is more than 975, so just 2.5% loss of fidelity. And even in this case, the 99% of the results are always so that's it. And going to conclusion. So what we showed that linear system identification works for two-level bosonic system, and can capture dynamics with a range of couplings. The polynomial optimization could be very promising and could be a tool to identify the dynamics when we have assumption about the part evolution. And we hope to use all these methods for real system, including the IBM quantum computer needs to possibly optimize function of quantum gates. So that's all. Thank you.
I think we have time for like one quick question. There's a question. There's a card. Any questions? I'll ask you a question. So what you were doing was for a qubit, right? But suppose you wanted to scale this to characterize the dynamics of larger number of qubits. It's going to get much harder, right? And doesn't it become like a computationally hard problem? Hasn't that been proved? Didn't somebody prove that? Like, are you familiar with the work of Toby Cubitt and Michael Wolf and Jens Iser? I think they proved some hardness results. We can talk about it after. All right. Thank you. So let's thank you for again.